All right. So this series of videos is going to introduce you to a type of reaction called electrophilic aromatic substitution. And what electrophilic aromatic substitution allows you to do is basically put substituents onto a benzene ring or onto an aromatic system. The general scheme for electrophilic aromatic substitution looks like this, and I'm just going to use benzene as our go-to aromatic compound right now. But what we're going to be doing is we're going to be taking benzene. Later on in this chapter, we'll be looking at substituted benzenes, but we'll be taking benzene and treating it with some electrophile, and I'm going to represent this electrophile as E plus. And then to counter the counter ion to that E plus is just going to be X minus, right? And when these react, what happens is you get a substitution where the hydrogen on the starting material is substituted with the electrophile, which is one of the reactants, right? And then you end up with an acid at the end of the reaction just to balance everything out. Now this is a really important reaction or class of reactions just because a lot of pharmaceutical compounds, top-selling pharmaceutical compounds, feature substituted, highly substituted benzene rings and other aromatic rings. Okay, so here is just a very, very small handful of many of the drugs that are on the market that contain aromatic rings. So let's go through this really quickly. So just to kind of give you some perspective, the reason why a lot of drugs have rings is because these aromatic rings can actually interact with the proteins in our body and also the DNA in our body. And that interaction occurs through something called pi stacking, where the pi electrons of these aromatic rings can interact with the pi electrons of other aromatic rings through something called pi stacking, where you have two aromatic rings which are planar, kind of stacked on top or stacked next to each other. And that stacking forms a lower energy interaction between those two molecules. So anyway, here you can see that we have seven different drugs. We'll just go through them really quickly, just talk about the features and point out the aromaticity in these compounds. So let's start in the upper left-hand corner. Sitagliptin, which is a diabetes 2 drug, right? So you can see that it features two aromatic rings, most notably this trifluorobenzyl unit down at the bottom. Ibrutinib fights B-cell cancers, most notably lymphocytic leukemia, right? And you can see that it features this fused heterocyclic aromatic unit here, as well as a couple of benzene rings. Rilpivirine is a non-nucleoside reverse transcriptase inhibitor, which is used to defend against HIV. Let's see here, and enzalutamide fights prostate cancer. Posaconazole is an antifungal agent and also is used to treat fungal infections in the body. Apixaban is an anticoagulant that's used, or an anti-clotting agent that's used to treat people at risk for stroke or for embolism. And then this one down at the bottom, vortioxetine, it treats major depressive disorder, right? So you can see the wide range of diseases or of imbalances that are treated or fixed with these drugs, right? So it's not just one disease where aromatic pharmaceutical compounds are used, but it's that really have an impact all over the body. So if you have a chance right now, just for practice, take a look at these drugs and see if you can count up the total number of aromatic rings in this, or aromatic units in this molecule, or on this slide. Also, maybe see if you could figure out the total number of benzene rings, right? So not all of the aromatic groups are benzene. So just take pause the video and take a minute and see if you can count that number. So if you pause the video and you counted, you should have come up with 20 total aromatic groups. This here would just count as one aromatic group because it's a fused bicyclic system, so we just count that as one aromatic group. And then 14 substituted benzene rings can be seen here. So let's go back. So a little terminology before we get started, just so that we're all on the same page and communicating in the same way. So we're going to be looking largely in this chapter at an arene or arenes or arene systems. And what an arene is basically just a general term for a aromatic hydrocarbon. So that aromatic hydrocarbon, that could be a ring of any size, really. We're going to focus on the six-membered rings and the substituted benzenes in this chapter. A couple of molecules that I think are important to know the structure and name of that are going to come up again and again. Obviously, benzene is one. And so that's just C6H6, right? If we put a methyl group onto benzene, this is a molecule, or this is a compound that you've worked with extensively in lab, and this is toluene, or just methylbenzene. If we put a hydroxy group on a benzene ring, that molecule is referred to as phenol, or phenol. If you replace that hydroxy group with a methoxy group, right, so rather than OH, CH3, this molecule is referred to as anisole. Replacing that with an amino group would give us a compound called aniline. And then I think the last one that's good to know is putting a ketone group or acetylating that benzene ring. And this is a compound we'll see again and again, and this is called acetophenone. So you're going to learn a series of different reactions, a series of different electrophilic aromatic substitutions. They're all mechanistically going to work the same way. Before we get into those mechanisms, though, I think it's kind of important to review the structure of benzene and the structure of aromatic systems, six-member aromatic systems, right? So remember, benzene is going to be a planar molecule, so all six of those carbons are in the same plane, and I want to look at it from the side view. So we're looking at it, so the plane is orthogonal to the sheet of this paper. The plane of the benzene ring is orthogonal to the sheet of this paper, right? So if I draw my benzene like this, kind of looking at it from the side view, or the side perspective, right? So this bond here is a bond that's closest toward you, right? And then these are going to be kind of coming out toward you right there. That pi electron density on this molecule exists above and below the plane of that six-membered ring, right? So the pi electron density, those 6 pi electrons that we represent as double bonds, exist above and below the plane of that of that ring. Now in this reaction, what happens mechanistically is we're going to take those pi electrons and react those pi electrons, or pull those pi electrons out of aromaticity to make a new bond to the electrophile. Right, so this is the general mechanism that all EAS reactions are going to follow. Right, when that new bond is made, because we're using the pi electrons to make that new bond, we're necessarily losing aromaticity, right? So we're starting with an aromatic compound. The electrons reach out and grab an electrophile, and so we're losing one pair or two of those 6 pi electrons, creating an sp3 center, and losing aromaticity, and creating what's called an intermediate ion, or sorry, an rhenium ion. Right, and this is just a positively charged ion. So in this first step, these pi electrons reach out. The electrophile is attached to this carbon, and because those pi electrons left this carbon, that carbon would get a positive charge. And this reaction ends or finishes when a base, in this case we'll use the counter ion X minus, it pulls a proton and the electrons are left behind, and that compound re-aromatizes. Right, so it's a two-step mechanism. Okay, and you can see it's a net substitution. So we're removing a hydrogen, right, or substituting a hydrogen with some electrophile. And it's important to note that even though this is a net substitution, it happens through 2 steps, and those 2 steps are an addition followed by an elimination. Right, so similar to carbonyl substitution, that net substitution is not direct, right, but it happens through a combination of an addition followed by an elimination. Now, the structure of benzene, right, when this benzene reacts with the electrophile, it's reacting through the pi electrons. Now, benzene is not a good nucleophile, right? That aromaticity stabilizes benzene or other aromatic compounds, so much so that the pi electrons are very unreactive. But when they do react, they're going to react so that they meet an electrophile on the top side or on the bottom side of the molecule. So they're not going to react over here, they're not going to react over there, they're going to react in the direction that they're, or wherever they're oriented on the molecule, so the top and the bottom. In the next video, we're going to take a closer look at the mechanism.